Thank you all very much. When astronaut Jim Lovell of Apollo 13 fame was circling the moon, he looked back at Earth and called our planet a grand oasis in the great vastness of space. That's extremely unusual eloquence for an astronaut. You're not going to hear any more of that, especially before 9 in the morning. What I would like to do is talk just a little bit about how I got into the space program and some of my experiences in the space program, and then spend some time talking about science and engineering education, and particularly girls and young women in science and engineering. And I'm also going to try to keep my remarks down to a reasonably long period of time, less than the 50 minutes of my physics lectures, and save some time for questions. I think there were 3x5 cards on your seats, and if anybody's got a question, I'm going to try to leave 15 minutes at the end. And so Lucy will come around about half an hour from now or so and just pick up the cards, and I'll try to answer as many of those questions as I can. Well, to quote Carl Sagan, "It's suicidal for a society that depends on science and technology to know nothing about science and technology." And as everyone in this room knows, science and technology are the engines that drive our economy. But the kids that are growing up in this country aren't studying science and math and engineering in the numbers that they are, the numbers that they should, just for the sake of our economy, but also in the numbers that they are in other countries. And this is our future. A lot of you in this room are the future of our country's economy, and we need to make sure that there's a pipeline coming up behind you. We need a technically trained workforce, and it's in our national interest to take advantage of all the available talent, whether it's male or female. Now, to set the stage just a little bit, let me tell you something about my background. You heard more about my college career than most people usually do. It is true that I started college at Swarthmore as a physics major. I dropped out of school in halfway through my sophomore year to try playing professional tennis. I was a competitive tennis player all the way through high school and college, played national circuit, and quickly discovered that with my forehand, I had a better career in science than I did in tennis. So I transferred to Stanford and stayed at Stanford for undergraduate and graduate degrees. And when I was just a couple of months away from finishing my PhD in physics at Stanford, I was sitting in the Stanford student cafeteria one morning, 8 in the morning on a Tuesday morning, reading the Stanford student newspaper, the Stanford Daily. Have we got any Stanford students in here? Yeah, okay. And I still remember to this day opening up the Daily and seeing in the lower right-hand corner of page 3 of the Stanford Daily an ad that NASA had put into the Daily saying that they were looking for applications for astronaut. Now, this was a really big deal at the time, and it was a big deal for a couple of reasons. It was the first time in more than 10 years that NASA had selected any new astronauts at all into the astronaut corps. And, of course, it was a big deal for another reason. This was the first time that NASA had announced that they intended to bring women as well as men into the astronaut corps. And, in fact, that's the reason that they put ads in the student newspapers and corporate newsletters around the country, because they knew that they needed to do outreach, and that if they didn't let the qualified women know that this opportunity was available, they'd never find out, and they wouldn't get the applications that they were looking for. So the moment I saw that ad, I knew that that's what I wanted to do. I ripped it out of the newspaper, tossed away all my applications for postdoc, and stuffed that into the first mailbox that I saw on my way back to the physics department. Turned out a lot of other people did the same thing. There were about 8,000 of us who applied for that. NASA selected 35 of us to be the first group that was of astronauts selected specifically for the Space Shuttle program. And we were to join the 20 or so astronauts who had been with NASA in the astronaut corps since the Apollo program, since the mid-1960s, actually. I guess that perhaps the moral of this story for all of you undergraduates is that it pays to read your student newspaper. Answer those ads. The group of 35 of us is actually pretty indicative of what NASA was looking for at the time and is still looking for in the astronaut corps, and it's a very broad base of talents. So of the 35, 15 astronauts had test pilot backgrounds, 20 astronauts had science and engineering backgrounds, and that group of 35 included the first 6 female astronauts. And today the astronaut corps is just about 25% female, which is a high percentage for a high-tech industry, as you all know. I should probably add that my father was without a doubt the happiest man on the planet when I was selected to be an astronaut. My father taught political science at Santa Monica College up in LA. And my father did not have a scientific bone in his body. And he was about to have a daughter with a PhD in astrophysics. My father didn't know what astrophysics was. My father couldn't explain to his friends what his daughter was about to do for a living. Then I became an astronaut. My father's problems were over. He understood it. Yeah, could explain it to his friends. Many of you may have the same problem as you're getting out of college. Well, the 35 of us new astronauts all packed our bags. We moved to Houston, Texas, to the Johnson Space Center, which is where astronauts go to live and work and train. And we got in line for our turn to fly in space. My turn came first on STS-7, the 7th flight of the space shuttle. So that was my first chance of 2 to rocket into space, going from a standing start on the launch pad to 17,500 miles an hour in 8.5 minutes. And I leave it to all of you to calculate the acceleration that's required there. Let me start now taking advantage of an advantage that astronauts have over a lot of other speakers, which is that we've got good pictures. So let me try to give you a sense of what it's like to be in space. I've picked one specific area to focus on, and that's what the Earth looks like. So as soon as we get through a couple just introductory slides to remind you about the Space Shuttle program, I'll start showing you a view of the Earth. This is, could you go back? Okay. This is what the shuttle looks like just a couple of seconds after ignition. You've all seen photographs that look just like this. As the countdown clock is going towards 0, at T-minus 7 seconds, the space shuttle's 3 main engines ignite. Those are the 3 white circles in the middle of the screen. They're burning liquid fuel, liquid hydrogen and liquid oxygen, that's carried in that big ugly orange tank. And there's nothing in that tank but liquid fuel that gets burned through those engines. But even though those are the most advanced and powerful rocket engines ever built, the 3 of them together don't have enough thrust to lift the shuttle off the launch pad. It actually strains at the bolts as the countdown clock goes towards 0 so that the computers can verify that the engines are working perfectly and that everything else is going fine with the shuttle before they allow the solid rockets to ignite. At 0, the 2 solid rockets on the side ignite, and then there's plenty of thrust. You just leap right off the launch pad. To give you an idea of how powerful those solid rockets are, they burn for 2 minutes. At the end of 2 minutes, they've run out of all their fuel. There's nothing in them but fuel. And at the end of those 2 minutes, you're already 25 miles away from the launch pad. It's another 6.5 minutes through the launch phase, just accelerating on the strength of the 3 engines until you're traveling 17,500 miles an hour. It's 5 miles a second, and you're weightless, orbiting the Earth and weightless in space. Next slide. Okay, I put this one in just to give you a sense of, first of all, what a typical space shuttle crew looks like, and also how little room there is inside the pressurized part of the space shuttle. We are stretched from one side of the cabin to the other, and we're as far from the camera as we can get. This is the crew from STS-7, and only one of us had ever been in space before. That's the commander, Bob Crippen, the second from the left. The other four of us were the first four from that group of 35 to get to go into space. And as I said, this is what a typical crew looks like these days. It's been a long time since the space shuttle's gone into space without at least one woman on board, often two, occasionally three, out of a crew of 5, 6, or 7 astronauts. So this is a typical, I'm happy to say, a typical looking crew photograph these days. There are a couple ways that we can prove that we took this while we were weightless in space instead of in a simulator on the ground, but probably the easiest is just look at where I've got my hands. I've got my right hand on Rick's shoulder and my left hand on his wrist. I'm actually holding Rick down, keeping him from floating up and ruining our crew picture. Next slide. Okay, you've all seen pictures that look like this too. This is what the shuttle looks like while it's in orbit. If you were going to fly from San Diego to San Francisco, you'd get in something the size of the space shuttle. But what would be the passenger section of an airliner is actually open to space. It's open to the vacuum. That's where we carry satellites, pieces of the space station, astronomical experiments, whatever we're carrying on that flight. The only pressurized part of the shuttle is the nose area, kind of the cockpit area of an airplane. And as you saw, there's not very much room up there. We took this picture on STS-7. We were the first ones to use the shuttle's robot arm that you can see in the picture there to grab a satellite that we had brought up with us, release the satellite into space. Then we did a lot of tests with the robot arm and flying the shuttle to and from something else that was also traveling 5 miles a second. And then we went and used the robot arm to grab the satellite out of orbit. We were the first ones to do that too, and then brought the satellite back with us. So that satellite carried a camera, and so we took a picture looking back at ourselves. So I'm in this picture somewhere. Actually, Mission Control accused us of spending millions and millions of taxpayer dollars putting the arm in the shape of a 7 so that everyone would know what crew took this picture. Next slide. Okay, I want to tell you just a little bit about, give you a sense of what the Earth looks like from the vantage point of an astronaut in the space shuttle or the space station, which is up in orbit right now. A lot of people imagine that we see this big blue marble and can see the whole Earth at once. Well, that was true for the Apollo astronauts who went to the moon, but the moon's 250,000 miles away. The space shuttle and space station orbit about 200 miles, 250 miles above the Earth. So we don't see the whole planet, but we get a great view, and the advantage that we have is that we can see a lot of details on the Earth. So this is what Florida looks like. Site of next year's Grace Hopper Conference is captured in this photograph. And there are a lot of different things that you can see. You can see a bank of clouds off the east coast of Florida. If you look closely, you can see Cape Canaveral jutting out into the Atlantic about halfway up the state. Take a look at the color of the water around Florida. You can see that it's kind of a light color blue. That's indicative of very shallow water compared to the darker blue of the deeper water. And actually, can we get the lights down just a little bit? Is that possible? That's great. Is that better? Okay. There's one thing that this photograph shows that shows reasonably well, that is one of the most striking sights to any astronaut the first time he or she looks out the window towards the horizon. So look towards the horizon, and you can see just below the black a really thin royal blue line. Goes all the way across the screen. That thin royal blue line is Earth's atmosphere. That's all there is of it. That's all that separates everything we know on this planet from the vacuum of space. And it's really drives home how fragile the atmosphere is, and therefore how fragile our existence on the planet is. Next slide. Now this is a picture looking straight down at Cape Canaveral and the Kennedy Space Center. I guess a good analogy is that if you go to Paris, you're supposed to come back with a picture of the Eiffel Tower. If you go into space, they actually don't let you back unless you've taken a picture of Cape Canaveral. So all astronauts have a picture that looks like this. But take a look at the detail you can see. You can see bridges across the rivers. You can see the runway that the space shuttle lands on. That's the white diagonal line about 2/3 of the way up the picture. And people who live in this part of Florida can actually pick out their favorite shopping mall in this photo. Next slide. Just a couple of the natural features that you can pick out. This is a picture looking through the Straits of Gibraltar at Spain on the left and North Africa on the right. And if you take a look at the southern part of Spain, you'll notice that it's just a light color brown, and that light color changes very abruptly to a much darker color. That line of abrupt color change is actually an earthquake fault. It's a fault that goes the width of Spain, and seismic features like that are actually very, very easy to see from space. Next slide. This is a part of the world that's been in the news a lot lately. This is a picture of the Middle East. That's the Mediterranean on the left part of the screen, and so you're looking at a picture of Israel, Jordan, Syria, a little corner of Egypt. Right in the middle of the screen, you see the small Sea of Galilee, and then directly below it is the kind of oblong-shaped Dead Sea. If you let your eyes go from the Sea of Galilee straight down to the Dead Sea, you'll notice that your eyes are following a linear feature. That linear feature is the Levantine Fault. It's a huge fault structure in the Middle East. It's the reason the Sea of Galilee is where it is. It's the reason the Dead Sea is where it is. And that same fault goes about 1,000 kilometers further south and actually opens to form the Red Sea. The different colors in this picture are just indicative of different types of rock and different ways the land is being used. And you can actually see drainage patterns in this photo too. So it gives you a sense of how useful this perspective is for monitoring natural resources. Next slide. This is what a hurricane looks like from space. This was a Category 4 hurricane that was active during my second flight. You can see the feeder bands of the hurricane pretty clearly, and then the next slide is actually going to be looking right down the eye of the hurricane. Next one. And here you're seeing all the way to the water of the Indian Ocean through the eye. Just look at the structure of the eye wall. This is just a great picture. I wish I had taken this picture. Next slide. Just a couple of the effects of civilization that you can see from space. This is a picture looking down at a corner of Portugal, and what you're seeing are the contrails of airplanes going in and out of Lisbon's International Airport that day. Next slide. This is a photograph looking from east to west, from bottom to top across Brazil. And the astronauts who took this picture thought they were taking a picture of kind of an overcast day in Brazil with the clouds being stopped by the Andes Mountains at the top and then a little corner of Earth's horizon. Turns out that what they were actually photographing was not an overcast day in Brazil, but a typical day during the dry season, and what they thought was an overcast layer of clouds was actually accumulated smoke and haze as a result of all the fires that were burning at that time that had been set to clear parts of the Amazon forest. And what they thought were individual just thunderclouds or puffy clouds were actually plumes of smoke over fires that were burning at the time. So you can look at this picture and count the fires. And that one big plume right in the middle of the screen was over an enormous fire that's as large as some of the very bad fires that we have here in the West, in Southern California, Northern California, Arizona. It's a huge fire. This is what Brazil looks like every day during the dry season. Next slide. Okay, this picture's in here just because I like it. This is what a sunset looks like from space. So when the space shuttle's in orbit, space shuttle, space station, they're traveling really fast. They're going around the world at 5 miles a second, 8 kilometers a second. If you do the math, that means you go around the planet once every 90 minutes. That means you're in sunlight for about 45 minutes, darkness for about 45 minutes. So you see one sunrise and one sunset every 90 minutes. or 16 sunrises and 16 sunsets every 24 hours. So we've all got photographs that look like this, too. But you can see why. It's really a beautiful sight, and it's amazing how much structure you can see in the atmosphere, the vertical structure of the atmosphere. See the different layers. You can see where the troposphere ends and the stratosphere begins. What you're looking at are enormous thunderstorms just silhouetted against the sky. Next slide. This is what the Earth looks like at night. You know, a lot of people have the image of astronauts floating at the window with their eyes glued to the sights during the daylight part of the orbit, and then quick getting back to work and doing all the things that the taxpayers are paying us to do during the nighttime part of the orbit. It turns out nothing could be further from the truth. We're actually at the windows all the time. And this is the reason. It's absolutely beautiful. This is a picture in the Midwestern United States. There are no big cities in this picture. These are all small cities. But you can look at them and see how the cities have grown, the general shape of the cities. If you look long enough, you can convince yourself you can see the roads connecting the cities. It's absolutely amazing how much detail you can see at night. And again, people who live in this part of the Midwest can probably pick out their favorite shopping mall and 7-Eleven in this photograph. One of my favorite sights looking down at Earth came during my second flight. We were an Earth observing flight, so all of our experiments were designed to study Earth. What that meant to us was that our windows were pointed at Earth all the time, so we had a great view. And we had one orbit that took us up the east coast of the United States at night, and we could look off in the distance and see Miami coming, and then trace the outline of the entire east coast of the U.S. in literally continuous lights, all the way from Miami north of Boston. Unbelievable sight. Took us about 5 minutes, by the way, to make it up the east coast of the United States. Next slide. Okay, I'd like to just change gears for a few minutes and talk about girls and women in science and engineering. You know, I was the first American woman that got to go into space, but as I said, now it's common. Female astronauts are 25% of the astronaut corps, but all you need to do is look around the technical workforce and you'll see that women are still significantly underrepresented. Today they make up about 11% of engineers, about 20% of scientists, a little more than 20% of scientists. Now, employers, all the sponsors of this event are furiously trying to recruit from college campuses. They'd like to bring the technically qualified women into the workforce to start improving those numbers and take advantage of the talent. But when they go to UC San Diego, where I teach, Stanford, Princeton, what they find is that the women aren't coming out of college with the technical degrees, particularly in engineering and the physical sciences, computer sciences, in the numbers that they could really easily absorb. So they talk to college presidents and they say, graduate more women, and the college presidents say, we'd love to, and we admit we lose our share, but they're not coming to us out of high school and declaring majors in engineering and computer science, in physics, in the numbers that we would really like. So the problem starts before college, as you all know. On the other hand, if you go back to elementary school and you walk into a fourth grade classroom, you'll find that there are as many girls interested in science and math as boys. And that's been true for a long time now. There have been studies about every 10 years for the last few decades asking fourth graders a series of questions, and one of the questions that they ask is, do you like science? And that's the way it's phrased. Consistently through that time, 68% of fourth grade boys say they like science, and 66% of fourth grade girls say they like science. So in fourth grade, there are two great messages for the country. One is 2/3 of the kids still like science and math. We haven't knocked it out of them yet. But the other message is, in fourth grade, it's as many girls as boys. But then starting in middle school, 5th, 6th, 7th, 8th grade, we start to lose both boys and girls, but we start to lose girls in significantly greater numbers than boys. And it's a trend that starts right there in middle school, and it continues all the way through the pipeline. Now, in middle school, the reasons that we lose more girls and young women than boys and young men throughout the pipeline is a series of very complex reasons. But in middle school, one of the principal reasons is societal. It's not interest. In 4th grade, they were interested. They told us they liked science. It's not aptitude. The test scores are the same. The grades are the same. It's really some of the lingering stereotypes, some of the peer pressure that they feel. You get to middle school, and some of us still remember it's really important to fit in. A lot of girls feel that pressure. Many don't, and just blast right through it and go on to become computer scientists, rocket scientists, electrical engineers, whatever. But it affects a significant number of the girls still today in middle school, where it may not be cool to be the smartest one in the math class. An 11-year-old girl who says that she wants to be a computer engineer may get a very different reaction from an 11-year-old boy who says exactly the same thing. That reaction could come from his peers, his friends, could come from his teachers, could come from parents. It's just not cool to say that you want to be an engineer, a computer scientist, or a physicist if you're a girl in middle school. So I think that part of the message is, and I know that you're all very well aware of this, it's really important to get rid of those last lingering stereotypes, and you're all a big part of that effort, because as the girls growing up see people like you, it puts a female face on computer science and computer engineering, and it makes them appreciate that these are normal-looking people. They used to be girls. They used to have cats and dogs, and they're not geeks who work in rooms with no windows and no doors all their lives, and none of them wear pocket protectors. It's really important to introduce girls to role models, to change the culture so that they're not getting these messages about science and engineering, to make them appreciate that science, engineering, computer science, that these are all very creative endeavors. They're all very collaborative. They all benefit from a diversity of perspectives and backgrounds. The more people, the more smart people you have trying to solve a problem, the better solution you're going to get. And it's important to build their self-confidence that they can go on to do these things. This is what motivated me to, I've been on leave of absence from UC San Diego for about 4 years now. I'm a professor of physics there, but I'm on leave of absence to start Sally Ride Science, to try to put some programs and materials in place that will help encourage kids in that upper elementary and middle school time frame, but with a particular focus on girls. So can we go back to the slides? And this is a picture at one of our science festivals. This one was at Caltech a year or so ago. We hold these on Saturdays at college campuses around the country. We did one at University of Michigan last weekend. We're going to be at Cal State LA in 2 weekends. We'll be up at NASA Ames in 3 weekends, in Houston in 4 weekends, University of Alabama in 6 weekends. And we get 1,000 girls to come out to these on Saturday afternoons. And it really shows that the girls are out there. They're really interested in this stuff. We do one at UCI every year that Deborah Richardson has helped us put together, and she can attest to the fact that these things are a lot of fun. The girls love it, and they love the computer science workshops, and they really get into this stuff. Next slide. We've also started creating booklets just to introduce girls to women who have gone on to careers in, this one happens to be engineering, but just show them that these are, again, real live people who are normal people. We'll show a photo of them as a kid, or a photo of them out on the beach, or a photo of them, at a computer, but just photos that they can relate to. and give them an introduction to these folks. Next slide. And this is a parent handbook that I think many of you may have gotten here. This was an NSF-funded handbook for parents, because parents can put very subtle pressures totally unconsciously on their daughters especially. And so we're trying to introduce them to the things that, introduce them to resources so they can support their daughters, and also give them some tips about how to how to encourage their daughters, and things maybe not to do that might subtly discourage them. Well, so do we expect this to work? If we put this focus on middle school, high school, college, and really try to change the landscape, do we expect this to work? And the answer is yes, and some historical perspective is really useful here. In 1970, which is a year that I started Stanford, so it's not the dark ages. There are some people here who remember 1970. In 1970, 5% of law school students were female, 8% of med school students were female, 3.5% of business school students were female, and this one's my personal favorite, 1 in 27 high school girls played sports. So in 1970, you could have concluded that women didn't want to become doctors, they didn't want to become lawyers, they weren't good at business, or they'd be going to business school, and they didn't like sports, or they'd be playing sports, because there were no obstacles, overt obstacles. But of course you would have been wrong. And hindsight shows you that, because now if you look at law school, it's 50% female. If you look at med school, it's 50% female. Business school, 45% of the MBAs last year went to women. Half of high school girls now play sports. So why should we think the same trend won't go on in physics, engineering, computer science? And part of the reason, particularly in engineering and physics, is just the stereotypes were so much more ingrained, and the numbers started so much lower in 1970 that although the numbers have been trending up, they still have a long ways to go. They've gone up from less than 1% in engineering in 1970 to 11% now. Now, that's a huge increase, but it's still got a long way to go. But why should we think that it's just going to flatten out and not continue to trend up? Computer science has been an interesting anomaly, because as I think you all know, I'm sure Shirley probably said this, that the numbers of undergraduates, the percentage of female undergraduates getting degrees in computer science has actually gone down since the 1980s. But again, I think that a lot of it is image, role models, and just keeping the kids in middle school and high school interested enough so they don't foreclose those options and just decide in 9th grade that this is, not for them. You need to keep their options open. So I think that the message here is one that you're all well aware of. There are lots of kids, and particularly lots of girls who are growing up right now, who can go on to do great things, who can go on to become physicists, they can go on to become astronauts, they can go on to become computer scientists, but they need support, they need encouragement, and they need role models. And all of you today can be role models to girls growing up. Don't underestimate the influence that you can have on an 11-year-old girl, on a 12-year-old girl, on a 14-year-old girl, because they look to you as examples of people who used to be girls, who have gone on and who love what they do. You're interested, you're excited about it, and you can really have an impact on the generation that's coming up after you. So let me just conclude with a little story to show you the impact that role models can have. This is a true story. This happened to me just a couple weeks after my first flight into space. And just to give you some background, because some of you may not remember my first flight quite as clearly as I do, or the publicity surrounding it. There was a huge amount of publicity surrounding the first flight, because this was the first time that a woman had ever been allowed to go into space. Okay, so there was magazine covers, TV, front page, newspapers, and it was all focused on the one woman on the flight. you would not have known that there were 4 guys on that flight if you'd just been watching the media. So with that background, about 2 weeks after we landed, I was having lunch with a friend in New York City, and someone that neither of us knew came up to the table and sat down with us and said, do you mind if I sit down? And we said, I guess apparently not. And she said, I've got to tell you a story. And she told the following story. She told us about her 5-year-old son who had just discovered, like 6 months before, the space program, as only 5-year-olds can. So he became completely engrossed in everything having to do with space. She had to buy him a flight suit. She had to buy him a helmet. He dressed up for Halloween as an astronaut. He knew the thrust of the engines on the space shuttle. And we were the first flight that was kind of on his horizon here, the first flight since he discovered space. So he was just looking forward to this, looking forward to this, looking forward to this. He made his mother get up at 3 in the morning to watch the TV while we, headed for the launch pad. He made her watch the entire countdown as we were counting down to lift off. We finally, from her perspective, probably got to 0. We took off. They all cheered. She went back to get ready to go to work. And about 2 minutes later, she heard him crying in the living room. And so she came running back in, thinking, has something gone wrong with the space shuttle? What's the matter? Are they okay? And he said, they're fine, they're fine. And he kept crying. And she said, well, what's the matter? And he looked up to her and he said, Mommy, can little boys grow up to be astronauts too? Thank you. Okay, so Lucy is doing me the honor of screening the questions. Let's see. Will the United States be globally competitive in technological advances in the next 20 to 30 years? If not, what actions need to be taken? Okay, so it's a great question. We in this country have a long, strong history of technological innovation. And as I said, science and technology, they're really the engines that drive our economy. They're what have made us the global force that we are. It's what has brought us the prosperity in this country. And I think that this is really an open question, and it's a question for your generation to answer, and particularly in the work that you do and the work that you do in helping to bring the next generations up. Because I think that we certainly have the intellectual potential to be globally competitive in technology. But we do not yet have a real national focus on the importance of science and technology education in maintaining that workforce that can maintain that global competitiveness. The corporations generally, and I think all the corporations that are sponsors here, they all get it, and they've been at the forefront of this. They understand that this is an education issue, this is a workforce issue, this is a mind share issue, and that we have to get the workforce of the future trained today, and we need to do something about the way science and math and engineering are perceived in this society and the way they're taught in this society. The government has not yet put a real strong focus on this, so it's not a mandate like it was back in 1957, which was the year of Sputnik, which just woke the U.S. up instantly and created a huge national emphasis on science and math education and on engineering. And we need to have something like that today to get this right into the forefront of people's minds. So I think we're at a critical time. The second one Can you discuss the latest news from Washington, D.C. concerning K-12 STEM education? Maybe. Latest news from Washington, D.C. is always it's always hard to know what the latest news actually is from Washington, D.C. You know, there are I would say pockets where there's a lot of emphasis put on this. NSF gets it. NSF understands how important K-12 STEM education is, whether it's formally in the schools or informally in out-of-school programs. And again, this is a workforce issue. NSF has a relatively small budget, particularly in this area. They do mostly, you know, they're mostly a research foundation. Other areas of the government get it, but again, there's not a good coalesced effort within the government to pool resources and to really influence policy. The Department of Education held a conference on girls in math and science that Lucy and I were both at back in May. It was a good conference that pulled together a lot of the right people who've been involved in this sort of thing for a long time. We're hopeful that something will come out of it. That was May. This is October, so we're maintaining our optimism. But I think that's probably gives you a good idea of the kind of the lay of the land. Okay, this question comes from your youngest member, youngest attendee, and the question is, how do you start the shuttle? You know, you got the picture of the ignition key, right? I mean, it's actually a great question because the whole countdown process, you know, just kind of it starts a couple of days before the space shuttle actually launches. The whole shuttle gets all ready. You have to load the fuel into the fuel tank. You have to make sure that all the computers are working properly, that all the valves are working properly, that all the electronics is working properly. And then when you decide to start the engines, and this is done with the computers, but there's a capability to stop it from everybody. But as the countdown clock, things are automated with the countdown clock. So as the countdown clock gets to T-minus 7 seconds, then valves open. They allow the hydrogen, liquid oxygen to come into the engines and mix. And as soon as that happens, liquid hydrogen, liquid oxygen burn, so you get the ignition of the engine. So it's at 7 seconds. Basically, the computers open those valves and feed the fuel into the engines. And then at 0, the computers actually allow sparkers, they're literally sparks, to ignite inside the solid rockets, and that ignites the solid rocket fuel. It just catches and essentially explodes, and you're on your way. It's a great question. Okay. Let's see what we got here. Okay, good. Okay. What do you think of space tourism? Don't you all wish you had $20 million to buy a ride in the space shuttle? You know, so I think it'll be a great day when everybody can have the same opportunity that I had. I mean, it's an unbelievable experience. Weightlessness is just fun. There's no other way to describe it. The view, as you saw, is spectacular. I think we're a ways away from that still. This really still is rocket science, so it's still hard to get people into space. But I think it's going to be a great day when people can take a vacation into orbit. I think I'd prefer that we find, if we're going to be taking extra people into space besides the professional astronauts, my preference would be that we find a merit-based system rather than the person with the biggest checkbook. But you know, you have to hand it to the Russian space program. They found a good way to bring in a little bit of extra money. through the space tourism program. So, and I know that those are all people who feel very passionately about space. In fact, the last space tourist, those of you may have noticed, was a female engineer. One of the women who's, I don't know exactly what her contribution was, but she's an entrepreneur, engineer by training, entrepreneur who made her apparently more than $20 million, a lot more, through voice over IP. So just shows you there's a future out there. Let's see. What do you see as the future of space exploration, and how, as computer scientists and engineers, can we contribute? This is also sort of a timely question. NASA is going through a transition now, starting to phase out the Space Shuttle program. The Space Shuttle is going to be retired in 2010. That's a good decision. Space Shuttle flew for the first time in 1981. Now, that's not a long time for airplanes to fly. There are a lot of airlines that fly that are older than that. But the shuttle was not made to be maintained and refurbished for that period of time. And because of that, you know, it really is time to retire the Space Shuttle. We're starting to come to the completion, slowly but surely, of the International Space Station. So the future of human exploration is now focused on getting us back to the moon by around 2018, and there's a big effort now to do that. And that is going to require a lot of design work, a lot of design challenges, a lot of simulations, large-scale simulations, particularly on the navigation, the aerodynamics of return, basically, you know, how you land these things, and simulations of environments on the moon and later on Mars. And I think probably looking off into the future just a little bit, but work is starting on it even today. You know, we really need, as we send people out to Mars or spacecraft, robotic spacecraft off into the solar system, we need to be able to get data back from them, and we need to be able to get large streams of data, much larger than we've been able to get before, back from them. So there's a considerable effort to talk about setting up kind of an interplanetary internet, so that we can communicate, get data back more routinely, and in you know, just with larger bandwidth. So I think that there's a huge amount of work to be done, a huge contribution to be made from computer scientists and engineers in space exploration, and it's in all the things that you might imagine around communication, data transfer, and simulation.
It goes back to me. I gave you the wrong.
Gave me the wrong ones.
Yeah, sorry.
Okay. What is the best memory from all flights? Okay, so we'll assume that we're talking about my best memory from my flights. And, you know, I think that probably the most striking memory is the instant of launch, because there is no way to simulate that. No, there is nothing like it anywhere. It's just the instant of launch. But probably the thing that there are two things that I look back on and just will never forget, and they're things that you cannot replicate on Earth. One is being weightless. Being weightless, as I said, it is just fun. And if you can imagine turning gravity off in this room, you know, you'd all float up into the middle of the room. You couldn't stand on the floor if you wanted to. You could do 32 somersaults in a row in the middle of the room. It is the best way to learn Newtonian mechanics, and every action has a reaction that there is, because, you know, you push off of somebody and you go one way and they go the other. The first time that I opened one of our lockers, right after we got into orbit on my first flight, the first thing you do is change out of the uncomfortable launch suits and into, you know, basically shorts and T-shirt for the rest of the flight. So we went down to a clothing locker, and it's just a pull-open locker. And you know, I went down, it's just a drawer, and I kind of floated down. My first experience floating, kind of floated down, made my way over to this locker, grabbed it, floating in the middle of the room pulled, and the locker didn't open. I went smashing into the locker. But I learned quickly. And then I think the other thing is the view of Earth, because it's unbelievable. It's absolutely spectacular, and it really does give you a different perspective. Let's see. I like this. This is a good one to end on, isn't it? Seriously, do you have or have you ever owned a Mustang? I have been running from that song since high school. And the problem is they keep redoing it. Thank you all very much.